Welcome to Electrical and Electronic Engineering Lecture Series. The anchor person is Professor Michael C. Ndinechi. Our topic today is computer arithmetic. Please follow me in this lecture series. By subscribing to my YouTube channel at https://youtube.com Ndinechi Michael C. You can also listen to my introductory lecture on computers in module 006, and you can also listen to other lectures on computers in module 014, part 1 to 7 at https://youtube.com Ndinechi Michael C. Our topic today, like we said in our advert, that it is computer arithmetic. So in digital computer circuits work with binary numbers and instructions coded in binary number form. Binary numbers contain only two different digits, zeros and ones. It is therefore very important that we develop an understanding of binary numbers, binary arithmetic, and instructions coded as binary patterns, so that we can begin to comprehend how computers operate. The total number of different digits used in a number system is known as the base or radix of the system. Other number systems widely used in connection with computer and which are closely related to binary or used to represent binary pattern are the octal. When we talk of octal, we are talking of base 8, and the decimal, which is base 10, commonly used by humans, and hexadecimal, which is base 16 numbers. In the binary system, numbers are written as a sequence of ones and zeros. 0 in the binary system may be represented by a single digit 0 or by multiple digits of zeros. Example, you can use 00 to represent 0. You can use 000 to represent 0. You can use 0000 to represent 0. No matter, they all represent 0. 1, on the other hand, represents powers of 2 raised to power something, like 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, and so on to 2 raised to power n, where n is an integer. It is the position of 1-digit binary number that has the following meaning. For instance, if you have a string of binary numbers, 1, 1, 1, 1, the 1 to the right, which is the least significant bit, has a power of 2 raised to power 0. The next one following it, as you move successively from the right to the left, has the power of 2 raised to power 1. The next 2 raised to power 2. The next 2 raised to power 3. And if you look at that, you see that it follows a pattern. 1, 2, 3, 4, 1, 2, 4, 8. 1, 2, 4, 8. So you say that the binary number 1111 is equal to decimal 1 plus 2, if you go from the right to the left, plus 4 plus 8, and so on. So say the right-hand bit is the least significant bit, while the left-hand bit is the most significant bit. As we progress from the right to the left, successive bits increase their weighting value in powers of 2. Therefore, if we consider a typical binary number 10101101, the weighting will be as follows. Starting from the right, which is the least significant bit, will be 2 raised to power 0. Then successively to the left will be 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, 2 raised to power 4, 2 raised to power 5, 2 raised to power 6, and 2 raised to power 7. So if you look at it, it means 2 raised to power 0 will always be 1, 2 raised to power 1 will always be 2, 2 raised to power 2 will always be 4, 2 raised to power 3 will always be 8, 2 raised to power 4 will always be 16, 2 raised to power 5 will always be 32, 2 raised to power 6 will always be 64, and 2 raised to power 7 will always be 28. If you go further to the left, you have 2 raised to power 8, which is 256. Further again, 2 raised to power 9, 512, 2 raised to power 10, 1024, and so on. So now, in the human form, you now convert that by noting where the power of 1 is. When you do that, you see that that binary digit will be equal to 173 in decimal number system. So what we have done is just to have wasted our time trying to do it as human beings or knowing how it is being done. The basic thing you need to do is, if you look at here, we say, so 10101101 in binary, when given such, because you already know that the weighting starting from the right-hand side, which is the least significant bit, is 1, the next one is 2, the next one is 4, the next one is 8, and so on. You just list that, put it under the number of binary digits given to you. Anywhere that is 0, you cancel it out. Anywhere that is 0, you cancel it out. In our example, 2 is under 0, 16 is under 0, 64 is under 0. You cancel them out and add the other one, it gives you the decimal equivalent. That is decimal base 10 equivalent. So all the things we have done before now is just to bring out what happens behind the scene. But for you as human being, it doesn't matter the quantity, the length of binary digits given to you. What you need to do is just to continue to list this under it and cancel the ones that are under 0 and add the other ones. It gives you exactly what you want. So now, just as we have looked at whole number, The computer can also handle binary fraction. So just as we use a decimal point to separate the whole and decimal fraction part of a decimal number, we can use a binary point in binary numbers to separate the whole and fractional part. The significance of the weighting of these bits behind the binary point is illustrated below. For instance, if we have 0.1111, you see that the one to the right, which we call the least significant bit, is having a power of -4 because we have 4 decimal places, which is the same thing as 1/16. The next one is having the power of -3. Likewise, the next one -2. Then the one closest to the decimal point is -1. So, just like before, you expand them, you will see that decimal, binary decimal 0.1111 will give you equivalent of 0.9375 in base 10. So, like we said, it doesn't matter the strength, list them and put this equivalent of weighting under them and cancel out the ones that are under 0. If you look at that example, say if we have 1101, the 0.5 is under 1, the 0.25 is under 1, the 0.125 is under 0, so we cancel it out. Then the next one, 0.0625 is under 1. We sum it, it will give us 0.8125 in base 10. So it's as straightforward as that. But we can go ahead to learn how to convert from decimal to binary. We say to do that, we do a systematic method of converting a decimal number into its equivalent binary number. It consists of dividing the decimal number successively by 2 and noting the remainders. The binary equivalent is then found by weighting these remainders in the reverse order. Take, for instance, we want to convert 12 in base 10 into binary. If we do that, 12, not 11, it becomes 12 divided by 2 will give you 6. What is the remainder? 0. 6 divided by 2 will give you 3. The remainder will be 0. 3 divided by 2 will give you 1. The remainder will be 1. 1 divided by 2 will give you 1, and the remainder will give you 0, and the remainder is 1. So you look at the remainders and go in upward direction. It becomes that 12 to base 10 will be equal to 1100 in base 2. Sorry, this bit should be 0. This bit should be 0. So octal numbers. So although digital computers handle binary ones and zero numbers with ease, we as humans find binary patterns difficult to handle. For this reason, octal, that is base 8, and hexadecimal, that is base 10 numbers, are frequently employed. Conversion from binary to octal and vice versa could be as easy as anything. To do that, you group the binary number given to you, starting from the least significant bit in groups of 3 bits. Then find the binary equivalent of the groups. The reverse process, that is octal to binary, consists simply of writing the 3-bit binary equivalent for each octal digit. For instance, we have a binary digit 1011100111. It's in base 2, and we want to convert it to base 8, which is octal. Like 011. The next one is 110. The next one is 101. If you do that, then you look at what is the equivalent of 011 in base 10. If you look at that, it's equal to 3. If you look at the conversion we tried up, you see that this first one has power of 1, the next one power of 2, the next one, which is 4 but is 0, means 2 plus 1, 3. Likewise here, if you convert it to decimal, it is 6. If you convert this to decimal, it is 5. So it gives you 568 in 563 in base 8. Now, to convert from base 8 to binary, what you need is look at the numbers. For instance, we have 4037 in base 8. So you look at 7. What is the equivalent of 7 in binary? It's 111. Equivalent of 3 is 011. Equivalent of 0 is 000, because we are grouping in threes. And the equivalent of 4 is 11100. So you see that 4037 in base 8 is automatically equal to 10000011111 in base 2. So we can also go ahead to convert binary to hexadecimal, which is base 16, or base 16 to base 10, which is decimal. It is just as simple and straightforward as what we have done under binary and under octal. We know that from the least significant bit given to you, it will be 16 raised to power 0, which is automatically 1. The next will be 16 raised to power 1, which is automatically 16. The other one will be 16 raised to power 2, which is 256. You continue like that down. If you continue like that down, you see that you can do similar thing by multiplying each weighting with the position of the bit. But before we do that, we know that in decimal, we count from 0 to 9, and we go back. For base 16, it means that we will count from 0 to 15 before going back. And for humans, it may be very, very difficult. So, base 16 numbers after 9, we begin to represent 10 with letter A, 11 with letter B, 12 with letter C, 13 with letter D, 14 with letter E, and 15 with letter F. That is to make life easy for humans, so that when you are working on base 16, if you see A in your mind, it means you are looking at 10. That is why also some calculators, we have letters A, B, C, D, E, F, just in case you want to use that calculator to do any calculation using base 16. So for you to convert binary to hex, you now have to group the binary number given to you into 4 groups, into a group of 4 or a group of 4 bits. For instance, we have that string of binary number to convert to hex. We start from the least significant figure, that is the one to the right, and group them in 4s, and now find their equivalent in the 16. For instance, if you look at the bit 1111, we say it's equivalent to F. F is equivalent to 15. So instead of putting 15 there, we put F. Now, if you look at that, you see that the first one, which is having a weighting of 1, means 1. The next one means 2. The next one means 4. The next one means 8. 8 plus 4 plus 2 plus 1 is equal to 15. Instead of us putting 15, we put F, which is representing 15 in hexadecimal. Likewise, the 1011 is representing 11, which is equivalent to B. So to convert back from the 16 to binary, we also look at each number and put the binary equivalent. Thank you for listening. This is the starting point. We want to see how you followed. We will announce when we will do the part 2 of this. With that part 2, you'll be able to see how computers use these numbers it has converted to do some logical decisions, because the computer is not just there to do the arithmetic of converting from one base to binary, but we know as humans, we feed in decimal numbers or base 8 or base 16 numbers. The computer will convert it to its binary equivalent, because the computer is a digital system that makes use of zeros and ones. After that, it will now start using that zeros and ones to do arithmetic calculations, to do logical decisions, and to do control manipulations. In our next lecture, that is what we'll be looking at. Thank you.